Okay, let's get started in talking about reactions in aqueous solutions. We can even start on the title slide, and I can tell you that aqueous solutions, what that means is that we're going to talk about reactions that are performed in water, right? So reactions that are performed in water as the solvent. Okay. Now, there are other liquids, other solvents that we can use in chemistry. In fact, if you take organic chemistry, you'll find there's all kinds of different solvents that can be used in chemistry. But I'll be honest with you, in General Chemistry 1 and in General Chemistry 2, we focus almost exclusively on reactions that are done in water, that is to say, aqueous reactions. So it's really important that you understand the content in Chapter 4. Well, let's get started here. It says that a solution is nothing more than a homogeneous mixture of two or more substances. What does homogeneous mean? Right? It means it's all uniform, completely uniform, all one phase. Let's say, for example, you were to take some Kool-Aid, and put it in a beaker. Well, the Kool-Aid crystals, when they're outside of the Kool-Aid drink, they're a solid. But when you mix them in with the water, it all becomes uniform, right? You don't have, unless you've made it too concentrated, you don't have water with some crystals floating in it. You can see, no, the particles actually dissolve. And so that's a homogeneous solution. It says here, you've got to know the difference between solute and solvent. And it says here, the solute is or are the substances or substance present in a smaller amount. So in your solution, whatever is present in a smaller amount is the solute. And it says that whatever is the solvent is the substance present in a larger amount. So say, for example, again, if we go back to the Kool-Aid example, it's mostly water. So water would be the solvent, and the Kool-Aid crystals, or the sugar, whatever you want to call it, would be the solute. Okay? Now here it says some examples. If you were to have a soft drink like Coke or Pepsi or Mountain Dew or whatever you like, the solvent in a soft drink is actually water, right? A soft drink's a liquid, and most of what a soft drink is water, but there's something else dissolved in there. Not only does it have sugar, right? It's got sucrose, which is a sweet sugar. It's also got carbon dioxide dissolved in there as well, right? In a carbonated beverage. Let's look at another example of a solution. Air. You might not think that air is a solution, but air is definitely a solution. And what would the solvent in air be? Well, this might not be intuitive to everybody, but what's present in the largest amount in air is actually nitrogen. You're like, what? Yeah, it's mostly nitrogen. It's like 70% nitrogen or something like that, okay? And you can see that solute are the molecules in atoms that are present in a smaller amount. So the oxygen that we get from the air is actually present in a smaller amount than the nitrogen. Then we have little bits of other gases like tiny amounts of argon and methane. So that's argon, and this is methane here. What else? If you've ever played around with solder before, if you've ever had to, I don't know, solder something that broke, an electronic device or something, well, solder is a solid, and solder is mostly made of lead, right? That is considered the solvent, but there's also some tin dissolved in there. And so those are some examples of solutions. And again, don't think that solutions have to be in a liquid. They can also be in a gas or a solid. These are all examples of solutions. Well, let's switch gears and talk about a specific type of solution, which is an electrolytic solution. And before we do that, we have to define what an electrolyte is, okay? So again, some more definitions that you have to know. It says here that an electrolyte is a substance that, when dissolved in water, results in a solution that can conduct electricity. Okay, so if we just have a beaker maybe with some water in it, okay, we have a beaker with some water, and if we put some solute into that beaker, and then it ends up being able to conduct electricity like this, that's going to be considered an electrolyte. So what it means is that the substance that you put in there was an electrolyte. Let me give you a little more detail on this diagram, just so you're sure about what the heck is going on. So you can see here that there's a beaker. Maybe I could choose a better color than that. You can see here that there is a beaker. Right here in all three of these pictures, there's a beaker. There's a solution inside the beaker. Okay, then you have a light bulb, and it's plugged into the wall somewhere. So it's plugged into the wall into a power outlet. But what might be a little bit harder to see, you can see it here better. You see there's two wires dangling from here, okay? Those are electrodes. And the only way for the light bulb to turn on is for this to be a closed circuit, okay? Would either be to connect the wires or to have them placed into something that can conduct electricity. So what an electrolyte is a substance that when you put it into the beaker, it allows the light bulb to light up because it allows the solution to what? To conduct electricity. Now, if you're like, well, what about, is there such thing as a solution that's non-electrolytic? Absolutely, okay? If you have a non-electrolyte, okay, a non-electrolyte is a substance that when you dissolve it in solution, it results in a solution that doesn't conduct electricity. I'll give you an example. Okay, maybe I should give you some examples. But anyhow, if you were to take table sugar, which is sucrose, and you made a solution of, delicious Kool-Aid or something, if you put the electrodes in that Kool-Aid solution, it is not going to light up the light bulb. So that tells you that Kool-Aid or sucrose is a non-electrolyte. Let me give you an example of something that is an electrolyte. Good old table salt, okay? So good old sodium chloride. If you were to put sodium chloride in here, it is an electrolyte. And we're going to discuss what makes it an electrolyte in a little bit. But it is an electrolyte, and it's going to allow the light bulb to conduct electricity. Now, some of you might be like, well, what about this guy here? It's like kind of, halfway it's in the middle, right? Well, that means that you must have a weak electrolyte in there, something that allows some conduction of electricity, or it could also be a dilute solution of a strong electrolyte, because as you dilute it, you have more less and less charged particles and a lesser and lesser ability for that solution to conduct electricity. All right. Now, if you might have some questions in your mind about, well, what exactly is an electrolyte made of? What exactly is an electrolyte? How will I know when I see one? Will I know, how will I know to recognize that? And in order for us to have an electrolyte, in order for something to conduct electricity in solution, it's got to be comprised of cations. So it's got to be comprised of cations and anions. All right. And in order you probably heard me say strong electrolyte and weak electrolyte in the last slide. Well, I said that. A strong electrolyte, and you need to know this, is an electrolyte that dissociates 100%. How do you tell the reader that it dissociates 100%? Well, let me tell you right now. It's when you have a unidirectional arrow. So we'll put here arrow in one direction, right? Harry Styles would love this, okay? So an arrow in one direction. That's how you know you have 100% dissociation. When you have a weak electrolyte, all a weak electrolyte means is that it's not going to dissociate 100%, okay? It's going to dissociate to some extent. Now, hear ye. This is just a function of Microsoft Word, okay? Because this is a big no-no. This arrow here, this is supposed to mean reversible reaction arrow, okay? So again, that tells us that it doesn't dissociate completely. Now, let me tell you what I meant by the heresy of this arrow, okay? This arrow is actually not the correct arrow, okay? This arrow that's shown right here, okay, that actually represents something in chemistry called resonance, okay? The correct arrow for equilibrium, okay, or reversible, or I can put here equilibrium, okay? The correct arrow for equilibrium is this. When you have a single-headed arrow, one pointing in each direction. So this is reversible, or it means equilibrium. Either one is fine. Okay, there we go. Again, and if you're like, Mr. Dion, why are you using this arrow then? Well, it's because it's the only thing I could get to work in Microsoft Word. I'm not that much of a guru. Anyhow, so what's the take-home message from this slide? An electrolyte is always going to be comprised of cations and anions. Look at sodium chloride. You get a sodium cation. You get a chloride anion. Look at the next molecule. This is called acetic acid. Acetic acid. It's going to dissociate to give you an anion. This is called the acetate anion, and it also dissociates to give you a proton. We'll talk more about that later on. But again, the electrolyte has to dissociate to give you a cation and an anion, If it's a strong electrolyte, it dissociates completely. If it's weak, you get partial dissociation or some dissociation, but it's not completely dissociated. All right, give me a thumbs up if you follow me so far. Just about electrolytes, not meant to be anything, really mind-boggling. Thanks, Reagan. Great. All right, perfect. Well, let's look at the next slide here. It says ionization. So this is getting back to that acetic acid. It says ionization of acetic acid, and here's the structure of it: CH3COOH. It's aqueous. Tells us it's a solution in water. Is in equilibrium with CH3COO minus. I'll remind you again. It's always good to remind your students about some polyatomic ions. So CH3COO minus. This is called the acetate ion. Okay, so we end up with acetate plus a proton or hydrogen ion. Now, as I said, that reversible arrow, which isn't even correct, okay, it should be this, but whatever, we're going to go with what we have. The reversible arrow represents, or the back and forth arrow represents a reversible reaction, and that means the reaction can occur frontwards and backwards. Acetic acid is a weak electrolyte because its ionization in water is incomplete. It doesn't completely give you, the acetate ion and a hydrogen ion. No, it gives you some, but not all. Okay, so that's a weak electrolyte. Now, let's take a look at some electrolytes here carefully. Again, we have a non-electrolyte, which doesn't conduct electricity. It doesn't give you cations and anions in solution. So this is just an example of a non-electrolyte. So this is glucose. Glucose is a non-electrolyte. You're like, what, sugar? Yeah, sugar is not an electrolyte, okay? Because when you take solid sugar and you put it in water to make an aqueous solution, it still remains intact. I don't see any cations and anions here, do you? Okay, I don't see a plus or a minus around the glucose. No, there isn't. It remains completely intact. And so glucose is not an electrolyte. Let's take a look at some examples of strong electrolytes. So we're going to start on this column right here with strong electrolytes. Well, what do we have? We have HCl, which is hydrochloric acid. Remember, these are aqueous solutions, so that means it must be hydrochloric acid. The next one is HNO3, that's nitric acid. The next one is HClO4, that's perchloric acid. Next, we have H2SO4, that's sulfuric acid. Then we have NaOH, that's sodium hydroxide. The next one is barium hydroxide. And basically, at the end, whoever was writing this slide got tired and just said, oh, come on, it's just ionic compounds, right? It just said ionic compounds are going to be strong electrolytes. Okay? So, strong electrolytes, to summarize, are going to be ionic compounds plus these acids and bases. Okay? And if you're like, which ones are acids and bases? Well, I can rehash that too. I can go over that again as well. Okay? These ones here, okay, these are acids. Okay? These are all strong acids. Not Strong's acids, strong acids. These are strong bases. Okay? And then other ionic compounds, like anything that's the combination of a metal and a non-metal, for example. Okay, let's move to the next column, which deals with weak electrolytes. The first one we already saw it, acetic acid. It's a weak electrolyte. It only partially dissociates in water. We have HF. HF is hydrofluoric acid. It is a weak acid. The next one is HNO2, which is nitrous acid. I'll even put the name in, so nitrous acid. The next one is ammonia, right? The first three, maybe I should have written that in red, because the first three weak electrolytes that they have here, these are all acids, okay? Ammonia is a base, okay? So ammonia is a base, and it's a weak electrolyte. And then it also says water. Water is a weak electrolyte. What? And you're like, well, Mr. Dio, didn't you say that if you had water, it wouldn't conduct electricity? Well, water, if you had a strong enough charge, or a strong enough current, I should say, I guess water might be able to conduct some electricity, but I just want you to know that water is an extremely weak electrolyte, okay? Very, very, very weak. And And if you've studied chemistry before, you might have heard of Kw, which is the ionization constant of water. So if you take the concentration of hydronium and the concentration of hydroxide and multiply them, you get 1 times 10 to the minus 14 molar. So both of them are 1 times 10 to the minus 7. Anyhow, and if you're like, what the heck are you talking about? Don't stress about it, because we'll look at it later on in the class. All right, and now let's look at the non-electrolytes, urea. So these are all, I can even help you with this, okay? What are these compounds? Urea, methanol, ethanol, glucose, sucrose, what do they have in common? These are all organic compounds. Now, that doesn't necessarily mean that only organic compounds are non-electrolytes, but organic compounds, generally speaking, are non-electrolytes. Okay, so let's move on from there, and let's talk about hydration, okay? Just need to talk about hydration for a second, because when we talk about ionic compounds, okay, being dissolved in water, why is it that we can take sodium chloride, and why does it dissolve in water so well? Okay, I don't know if you've ever tried this at home. It's not a very expensive experiment. If you take some table salt and start putting it in water, you'll find that you can dissolve quite a bit of salt in water, right? It dissolves quite readily. It takes a lot of salt before it starts to not be able to go into solution. So, and if you're like, what are you talking about, Mr. Dean? All I mean is this. If you take sodium chloride, right, solid sodium chloride, and you put it in water, so that's what I'm representing up here, you end up with sodium ions, okay, and you end up with chloride ions. Now, how could I just write this out like this? Well, I told you a couple of slides ago that, what? Ionic compounds are strong electrolytes. So that's why sodium chloride is an ionic compound made of a metal and a non-metal ionic compound. That's why I can take the liberty to write this reaction arrow in one direction, and I end up with a sodium cation and a chloride anion. Now, what I'm trying to get at in this slide is what makes water so special? Like, why do we spend all our time talking about water in general chemistry? Can't you think of something cooler? Well, no. Water is actually very fascinating, what it can do. And if you look at the structure of water, it has what's called a dipole, and that's what's represented by this arrow here. And that's also what's represented by these partial charges here. So that delta sign, the Greek symbol delta, means partial. Okay, so what it tells us is that if this is H2O, so you have oxygen bound to 2 hydrogens, it tells us that the oxygen is partially negative, right? It's got some negative character. It's not an anion, but it's got some negative character. And then on the other side of the molecule where the 2 hydrogens are, there is some partial positive character. Now you might be like, okay, water, partial positive, partial negative. What makes that so great? Here's the cool part, okay? Here's where it gets really interesting. If you take a cation, like your sodium cation or any cation, so cation, and you put it in water, why does it just do this, okay? It's because the water molecule interacts with the cation. You see the positive charge here? Do you notice how all the water molecules are all pointing in the same direction? Well, most of them, at least the ones that are very close. You can see they're all pointing in the same direction, right? How are they pointing? They're all pointing with the partial negative charge towards that positive charge of the cation. What do we know about opposite charges? They attract each other. And so what that does is it stabilizes that cation. It's not just floating all willy-nilly in the water. No, it's being stabilized by the water. And that enables the sodium chloride crystal to break up. Similarly, with the chloride anion, here's the negative charge right here. You notice that the water molecules that are around it, you notice that it has the positive, the delta positive, right? Those are closer to the anion, right? So that they can stabilize the negative charge. So if you think about it, what's being said here in this slide is that water has both a partial negative portion on its molecule by the oxygen atom. It also has a partial positive portion on the 2 hydrogen atoms. And since it's got that dual nature of being partially positive and partially negative, the water molecule can align itself with a cation or an anion and serve to stabilize it. Give me a thumbs up if you follow me on that. Water being so special. All right. Tyler says thumbs up. All right. And Shay, good. We're cooking with gas, okay? It's one of the coolest things about water is that it can stabilize both cations and anions. In fact, the university where I did my undergraduate degree, there was a professor there that all he did his entire life's work was studying water. And you're like, wow, that guy sounds really exciting. You know, he was very exciting. Anywho, let's move on to the next slide and talk about precipitation reactions. Real classic in chemistry class. You see there's some pretty color here. You're like, no, that's not an aqueous solution. Well, no, it looks like there's an aqueous solution up here maybe, but you can also see that there's some solid formed here. And when we form a solid, okay, that is called a precipitate. So I'll abbreviate it PPT. So we could call it, we say here, the precipitate, or as I call it sometimes, the PPT, is the insoluble solid that separates from solution. Now, if you're like, well, when do I get these insoluble solids? Well, we're going to get to that. That's part of what we're looking at tonight is we're trying to explain why do we get insoluble compounds formed in a solution. Now, it tells us here in this bullet point, it says, if you take lead nitrate, it should say lead 2 nitrate. What kind of hobo wrote this slide, okay? It should say lead 2 nitrate. Lead 2 nitrate reacts with sodium iodide to produce lead 2 iodide, is what it should say, and sodium nitrate. Then it says, write the molecular, total ionic, and net ionic equations. Now, you're probably like, what? You haven't even taught us this, and you're asking us the question? Well, let me show you what these mean, okay? A molecular equation is when you just write out the entire reaction, okay? You just write out everything. And it's telling you that you have a solution of lead 2 nitrate. What's the formula for lead 2 nitrate? Well, you should be able to put that together. Lead 2 nitrate is PbNO3, and you have 2 NO3, so PbNO3 2 reacts with sodium iodide. Sodium is in group 1A, likes to have a charge of +1. Iodide is a halogen. It's in group 7A, likes to have a charge of -1. And so we get NaI, and we end up producing lead 2 iodide, shown here, and we also get sodium nitrate. All right, so sodium nitrate. Now, somebody went ahead, and that somebody was me, and I went ahead and I already balanced the equation. So now we have a balanced equation. So again, a molecular equation is where we just have all the reactants written out. We don't leave the phases out. We make sure to include aqueous, aqueous, aqueous. Now looky here. It says that the lead 2 iodide is a solid. So that's our precipitate, right? And that's kind of the subject of this slide. Now you're probably saying, well, Mr. Dion, how did you know to write, AQ, and how did you know that PbI2, that lead 2 iodide, was a solid? Well, I'm going to show you that in a second. Okay? But before we do that, I want to introduce you to 2 more concepts. The total ionic equation. What we do is we break apart, we break all aqueous compounds into their ions. Okay? So if I look at lead 2 nitrate, right here, you see that it says AQ at the end? That means that in my ionic equation, I'm going to write it out in its ions. Okay, so everything that's AQ. So I have a lead 2 ion, I have a nitrate ion, and I have 2 of those. I go to the sodium iodide, I see that that's aqueous. I have 2 sodium cations, they're aqueous. I have 2 iodides, they're aqueous. Now I go to the other side. I do not break up anything that is solid, okay? So it says here in my green writing, it says break all aqueous compounds into their ions. I'll write in red. Not solids, okay? So if you have a solid like this, you're going to leave it. And you still might be asking, well, Mr. Dion, how did you know it was solid? Hold on, we're going to get there. So we leave the solid compound intact. Then you see that we have 2 sodium nitrates. It's aqueous. And so we're going to break that into 2 sodium cations and 2, oops, that's not balanced, is it? It should say should say 2 nitrate anions like that. Okay, that's the total ionic equation. We got one more to go. And I promise that this one is the easy of all of them. Then you write out what's called a net ionic equation. And to write out a net ionic equation, you cancel all spectator ions. And you're like, well, what's a spectator ion? Okay, ions that do not change. It means ions that didn't change from product side and reactant side. Look, I have lead 2 plus over here. My lead here is in a compound, so that's not a spectator. That did something. That changed. I look at 2 nitrates, and I have 2 nitrates here. That's a spectator. It didn't do diddly squat. It didn't change throughout the reaction. So I'm going to cancel those 2 out. I see that I have 2 sodiums on each side. Those are spectators. They didn't change. There's still 2 sodium cations. And then I also see that I have 2 iodides here, but my iodine here is in solid lead 2 iodide. So that's not a spectator ion. So in my total my net ionic equation, I'm going to write out what's left over. Well, what is left over? I got lead 2 plus, I got 2 iodides, and then I end up with lead 2 iodide like that. So that's your net ionic equation. The molecular equation, sometimes I like to call that the ME, because I can't write a molecular equation. Then I like to put TIE for the total ionic, and then NIE for the net ionic equation. Anyhow. Okay, give me a thumbs up if you follow me even part of the way on this, because we're going to give this a try this evening. But before we do that, I want to talk a little bit more about the precipitation of the lead 2 iodide, and I also want to talk about how the heck I knew that I ended up with a solid in the reaction, right? How did I know that I was going to end up with solid lead 2 iodide? Well, I mean, you do it for enough years and eventually you remember it, but most of you probably aren't going to become chemistry teachers, so I don't expect you to memorize everything under the sun. But what's happening in this reaction mixture, if you look over here, you see that you have to kind of look carefully here, but we have iodide ions right here. We have potassium. Well, that's not really showing the same reaction, is it? Anyhow, it doesn't matter. This would be potassium nitrate instead of sodium nitrate. I don't know why I couldn't get that together. Anyhow, but you see that you have ions that are not participating, right? I'll highlight them in yellow. I have this ion and this ion. These ones, sorry, you have green ions and nitrate ions. Okay, let me start over. So you have this ion, and those remain unchanged. But if you look carefully, you'll notice that the ions that I'm highlighting in green, the iodide ion, okay, and the lead ion, those are now together in a crystal lattice. This is a, let me write it in ink you can see, this is a solid right here, and it's yellow when you look at it with the naked eye. So there's the yellow solid. So this is lead 2 iodide, and you put solid like that, PbI2 solid. Okay, now let's talk about this whole solubility thing and how do we know when something is soluble? How do we know when something's insoluble? Well, let's talk about 2 different compounds, okay? We're going to talk about sodium nitrate, and we'll talk about lead 2 iodide. If you remember from the example that we just looked at, we said that sodium nitrate was aqueous, and we said that lead 2 iodide was solid. And the way that I knew that was by looking at this table of solubility rules for common ionic compounds in water. Okay? So it says here, solubility is the maximum amount of a solute that will dissolve in a given quantity of a solvent at a specific temperature. If you think about this, you know, a silly example, it might not be that silly. When I was a kid, I used to go to my next door neighbor's house after school. We'd play hockey, you know, street hockey and stuff. And sometimes we would make Kool-Aid, and we'd add so many crystals that eventually it wasn't homogeneous anymore. You could actually see the solid Kool-Aid, right? It was way too concentrated. But the idea is that we had surpassed the solubility of the Kool-Aid in water, right? We had gone past that maximum amount of solute. So if you are able to measure that exact amount of solute that could be dissolved in water, of a particular solute, I should say, that would be that solute's solubility in water. Okay, Now let's move on and talk about this table, table 4.2, the solubility rules for common ionic compounds. It's not that difficult. I will provide this to you on an exam if you need it, okay? And the way you do it is like this. Let's say you had a compound like sodium nitrate. Hey, what do you know? It's right here. You would look at the table and you'd say, okay, soluble compounds. Compounds containing an alkali metal. Hey, what do you know? Sodium nitrate has an alkali metal, right? It's got sodium in it, okay? So compounds containing the alkali metal ions, lithium, sodium, potassium, rubidium, cesium, or the ammonium ion are soluble. And there's no exceptions, none. So that's why I knew that I could put AQ, because AQ means that it is soluble. Okay, let's erase some of this spinach and talk about the other compound. Okay, the other compound is lead 2 iodide. Well, if I go back to the table and I look, nothing about lead iodide here, nothing about lead or iodides, nothing about lead or iodides, nothing here. Oh, hold on, halides. Ooh, okay. It says halides, chloride, bromide, and what? Iodide. Look, I have iodide in my compound. Okay. It says, hey, it's soluble. But then I have to go over to the insoluble exceptions and look here. Halides of silver. Sorry, I'm not seeing double here. It says silver twice, but yeah. Halides of silver, mercury, or lead 2. Oh, look, this is what? This is lead 2 plus right here. And since this is on the insoluble side, I know that it is not soluble, right? And I am going to put solid next to it like this. Okay, so not soluble. Okay, I'm not going to walk you through the entire, compound from soup to nuts, okay? But let's try one more compound. Let's say we had, I'll just write it here. Let's say we had this NH4. Oops. Could you guys tell me, is this compound soluble or not? Not a trick question. Could anybody tell me if this is soluble? Just write soluble or insoluble. That will do it. All right. Shay says soluble. I agree with you, Shay. Yeah. Other people say soluble. Some people are saying insoluble. Well, let's take a look. It says here in the table that insoluble compounds. Hey, this compound is called ammonium carbonate. Well, let's see here. Carbonates. Hey, carbonates are insoluble. Okay, cool. Let's go over to the exceptions. Compounds containing alkali metals. Ammonium isn't an alkali metal. Oops. And the ammonium ion. So that tells us that this is an exception and it must be soluble. And so we're going to put AQ like that. Okay. Well, let's try one more. Why don't we do, I don't know. Let's do silver sulfate. So I'll write it over here. If we had Ag2SO4. Could anybody tell me if silver sulfate is soluble or insoluble? Silver sulfate. Yeah, exactly. It's insoluble. Thank you. Good. Because why? You go over here to sulfates. Hey, look, they're soluble. Let's go over to the exceptions, and you see that silver is an exception and silver is insoluble. And so for silver sulfate, you'd put solid like that. There you go. You know how to use the table. I will provide you this table on your next exam because you might need it to solve a problem or two. But yeah, that's all there is to using the table. And you know what? The more practice problems that you do, the more accustomed you are to using this table, the easier it gets to use, and the more you'll be able to just look at compounds and say, hey, that's always soluble. In fact, I've taught this class before where I actually asked students to memorize parts of the table. Anyhow, but again, I'll provide it to you. Hey, the next slide's just kind of a fun one. Just kind of an FYI thing. Here's some examples of some pretty insoluble compounds, and you can see that not only do they form, different types of solids, but they have different colors, and you're like, well, how would you describe these? I don't know. I'd say that this one here, cadmium sulfide, looks kind of like, I don't know, an orange powder maybe. The lead 2 sulfide kind of looks like black. You can see it kind of looks like black crystals, maybe. Nickel 2 hydroxide. It's kind of like a green, white, I don't know, amorphous solid. And the same thing with aluminum hydroxide. That's a white, a milky white precipitate, maybe. Anyhow, so these insoluble compounds, what's so cool about these is once you get used to them and you've worked with enough of them that you can just look at a reaction quickly and say, hey, this cation or anion is probably present in this compound. In fact, making insoluble compounds can actually be a way to identify different cations and anions. Anyhow, that's not the subject of this tonight's lecture, but you guys probably have the slides. I'm not going to rifle back. I'm going to give you a second. We already did silver sulfate. We already did this one. We said that this is insoluble. So we would put solid by that. I'll give you a second to try the next two. See if you can come up with an answer for calcium carbonate and sodium phosphate. I'll just throw it out there. Does anybody have an answer for calcium carbonate? CaCO3. Calcium carbonate. Anybody? I'm making the assumption that you have the slides printed out. Am I assuming too much? All right, well, I'll help you out. Calcium carbonate is insoluble, solid, and sodium phosphate is soluble. All right, so that means it's aqueous. All right, let's move on from there and talk about writing those net ionic equations like I just looked at. Okay, I tried to walk you through it before and kind of explain to you how it worked and everything, but now I want to take a hard look at the actual rules that you can use if you're ever stuck when you're trying some practice problems at home. You're like, what are the rules for writing net ionic equations? Well, the first thing is always to start with a balanced molecular equation. Then we write the ionic equation showing all strong electrolytes completely dissociated. So what is completely dissociated? That means we write them all as their ions, and we put AQ by anything that's a strong electrolyte. Then after we've written out the ionic equation, we cancel the spectator ions. And again, the spectator ions are the ions that were unchanged, right? So ions that are unchanged. We don't change those. So those are spectators. Then we check that the charges and the number of atoms are balanced in the net ionic equation. Boom. And then we write out the net ionic equation. Well, with that in mind, let's give the old college try here. And let's see. So this is a question where we're not only going to write out a molecular net ionic equation, but we're also going to use the solubility table. Okay, so let's see what's going on here. It says, predict what happens when a potassium phosphate solution is mixed with a calcium nitrate solution. Write a net ionic equation for the reaction. Well, the first thing we need to do is to be able to come up with the formula for potassium phosphate. You should know that phosphate is PO4 3 minus, and the potassium is K plus, and so potassium phosphate is K3PO4. Okay, it tells us it's a solution, so we know that it's going to be AQ, so we can put that in there. Now we're adding it to a calcium nitrate solution. Calcium is Ca2 plus, nitrate is NO3 2 minus, and so we'll write CaNO3 2 aqueous. Now we need to figure out what the products are. What are we going to do here? This is what's called a double replacement reaction or a double displacement reaction. We are going to swap the cations and we're going to swap the anions. So that means that potassium is going to go with nitrate and calcium is going to go with phosphate. So let's write those out. The first one that we're going to write out is potassium nitrate, and potassium has a charge of +1, nitrate has a charge of -1, so we have KNO3. We're going to look it up in the solubility table in a second, and then we're going to have calcium phosphate, which is Ca3PO4,2, and we need to look that up as well. Let's go back to the table, and we have two compounds of interest. I'm going to erase some of this spinach here. Erase some of this stuff so that we can see a little bit clearer. And the compounds we're evaluating are potassium nitrate and calcium phosphate. Okay, potassium nitrate. Well, it says here, all soluble compounds containing alkali metal ions, K+, no exceptions. So this is going to be aqueous. We're going to do the same thing for phosphates. We go down here, phosphates. Phosphates are insoluble. It says soluble exceptions, compound containing alkali metal ions in the ammonium. Calcium is an alkaline earth. It is not an alkali metal, and so this is solid. Now we can put that into our equation. So by potassium nitrate, we're going to put aqueous, and by calcium phosphate, we'll put solid like that. Now we need to balance out the equation. I have 3 potassiums over here, so I need at least a 3 over here. Like that. I've got 1 phosphate here. I've got 2 phosphates over here. So that means I need at least a 2 in front of here like this. If I have a 2, that means I'm going to have to double the amount of potassium to balance that back out. So now I fixed that. I have 3 calciums, so I'm going to need at least a 3 in front of there like that. And then if you look, the nitrate has balanced itself out because I have 3. Look, I have 3 times 2 nitrates, and here I have 6 nitrates. So 3 times 2 is 6, and 6 is 6. So there we go. So there's our balanced equation. So this is our molecular equation. I'll abbreviate it like that. And now we're going to write out our total ionic equation. Okay, so now we're going to take everything that's aqueous, this, and this, and we're going to break all 3 of those apart into their ions. Let's do it carefully. Well, how many potassium ions do I have in my 2 formula units of potassium phosphate? How many total potassiums do I have in that 2 moles? How many potassiums total do I have in 2 potassium phosphates? Yes, thanks, Chris. I have a total of 6, right? I have a total of 6 because I have 2 times 3. So I have 6 K plus aqueous, plus I have 2 phosphates, PO4 3 minus aqueous, plus I have 3 calciums, 2 plus aqueous, plus I have 6 nitrates because I have 3 times 2. So that's a total of 6 NO3 minus aqueous. And then what do I produce? I produce 6 K plus aqueous plus 6 nitrates aqueous plus Ca3 PO4 to solid. Now what are my spectator ions here? I can see that the potassium remained unchanged, and I see that the nitrate remained unchanged. So that now when I want to write out my net ionic equation, okay, I'm going to write what's left over. By tradition, I always write the cation first, and so it's going to be 3 calcium, 2 plus aqueous, plus 2 PO4 3 minus aqueous gives you Ca3 PO4 calcium phosphate as a solid. All right, and this is the reaction. This is the calcium phosphate precipitate, and here it's a white solid. All right, give me a thumbs up if you follow me on that. Or even if you're like, I think I could do it if I had a little bit of practice. Yeah, it always takes a while to practice your net ionic equations. Look, before we keep going here, I want to remind you of one more thing that I've reminded you of several times throughout this class. I'll probably do it again and again, is that in order to master this content, it's not even as complex as some of the math problems that we've looked at. What do you need to know? You need to be confident that you know what a phosphate is. You need to be confident that you know what a nitrate is. You need to be confident that you know that a calcium has a 2+ charge because it's an alkaline earth. You got to be confident that you know that potassium has a +1 charge because it's an alkali metal, right? So you've really got to be solid, rock solid on your polyatomic ions and your ions from the periodic table. Okay, that's quite a while. Who's interested in having a short break besides me? I'm really thirsty. Okay, somebody says yes, please. Yeah, I agree. That's a long time. Excuse me. Why don't we take a 15-minute break? We've earned it. We're a little bit ahead. I'm going to stop recording. So tonight, I'll be posting 3 videos to my YouTube channel. So the first one, which was the end of chapter 3, this one, which is the first part of chapter 4 that we're doing tonight. And then when I come back, I'll start recording again. And that way you don't have a big gap, of silence in the middle. All right, so it's 6:21. So how about around 6:35, we come back, we take a break here and just kind of give our brains a rest just for a second, and then we'll